Okay, so the spring scale in the diagram, which part of it? All of it, or?
No, it's just the last part.
The cart now moves towards the right with an acceleration toward the right of 5.5 meters per second square. What does the spring scale read?
So I know the acceleration it provides when it's just the spring scale FA column. I know the newtons for FA, and I know the total newtons, or the total acceleration. So how do I go about finding the
So now you have two spring scales pulling it?
Yeah.
Okay, so this is the problem. Looks like this. You've got the cart. You have two spring scales. That's a terrible spring. My goodness. What's that? Oh, yes. So you have these two spring scales. This is number 12 on the lab that I'm answering a question about. And you're pulling with two spring scales. We're pulling with an equal force on each. So half of the force is on one, half of the force is on the other. So this is going to be force over 2. And this is force over 2.
I don't think it's pulling equal, is it? It just says that the first one's still reading 10.5.
A spring scale in the diameter is 10.5. Cart moves to the right with an acceleration of 3.25. Two forces with two different spring scales. Oh, right. So it doesn't tell you they're equal. So this is excuse me. So the top one is FA. The bottom one is FB. And FA is still given at 10.5 newtons. So FA force equals 10.5. And that equals the mass times the acceleration, and you can calculate the mass from that, right?
Oh, okay. I think I can get it now. I can figure out the cart's mass.
Because once you figure out the cart's mass, you can figure out what the other one is, right?
Yep.
So that's mass times acceleration right there.
Okay.
Force equals mass times acceleration. And then when they pull with the other force, the other scale, FB, it gives you a total acceleration of 5.5 meters per second, which means FB is going to equal this mass from the first one, plugged in after you solve for that mass. You plug that mass in down here, and you put in the remainder of 5.5 minus 3.25. So you put in 2.25 meters per second. That's how much acceleration is caused by this force, right?
Okay. And your mass would be in kilograms, right?
That's correct. Then you can solve for force B. Okay?
Thank you.
You're welcome. Now, what else should we work on? Who else has a question about a homework problem?
I do.
Well, tell us what you want to do.
Number 1 with the chapter 5 homework, when it asks for the force of friction acting on the cart, I just was not able to get that, and I don't know There's a couple reasons why I'm not sure, but we can just go over it, I suppose.
I think I need to update my web browser because it's giving me fits.
I redid that question and I ended up getting the answer. So
You redid.
the number 9 that you were
Oh,
just on.
good.
And then I started to do 29 and 30. I think you accidentally closed 4.
Did I?
Yeah, I'm not able to, I don't see it on the page. I can't open it.
Well, let's see here, shall we? Whoa, 10, 16. Ah. Okay. All right.
Okay, thank you.
Chapter 5, number 1. So here we have a cart and a force and a mass, an acceleration. And so let's take a look. Apparently there's a frictional force in this problem, so we need to set up our problem with a friction in it. Okay. So this is what it's going to look like. We're going to have our cart. Wheels. We're going to have 2 forces on it. We're going to have a force of Ernesto. We'll call it force 1. We'll have another person pushing with some other force, force 2. And they're pushing the car. What other forces are involved here? I'll give you a clue. It's rolling along the ground.
Friction.
Frictional force. Which way is the frictional force going to be pointing?
Opposite of the normal
So if
force.
it's pushing this, if they're pushing the cart to the right, then that frictional force is going to push to the left here at the ground, where the ground contacts the wheels. We'll call that little f. Right? And Newton's law said this is one dimension. This is the x direction, positive x direction. And in one dimension, Newton says that if we add all the forces together, what do we get? What do they equal?
Net force,
Net force equals
mass times acceleration.
mass times acceleration. This is the same thing. This sum of the forces is the same thing as saying the net force. And then this equals also mass times acceleration, right? They've given us the mass, they've given us the acceleration, and the only thing that they haven't given us is one of the forces. So on the left side of the equation, we'll have F1, which is a positive force. We'll have F2, positive force. The friction is a negative force, and they've given us these 2 forces, haven't they? But they haven't given us the frictional force.
And the force 1 and force 2 are just given together as the force that I know.
So they're telling us the total force of both of them?
I think so, yeah.
That's fine. So the number that they give you for the total force of both of them, you just plug in for these two numbers. You'll plug in a number in. And then you're gonna have this subtract little f equals mass times acceleration. Well, the first part of this problem asks for the net force. Well, the net force is the stuff on this side of the equation, so you're gonna have to solve for little f first. So you solve this equation for the friction, and then you take that total force and subtract off that frictional force, and that will give you the net force. So, in other words, net force equals the force that they give you, the force in the problem, minus the frictional force that you solve for over here. Does that make sense?
Yes.
And that frictional force will be given in newtons, right?
All forces can be measured in newtons. You know, if they give it to you in pounds, then you have to convert to newtons. But all forces can be measured in newtons.
Now, in the first half of that problem, it's asking what's the net force acting on the part that's given
Okay.
What's the net when it's asking for the net force?
acting on the part that's the force that they give you that's connected to lambda, right?
Yeah, and then you subtract off the friction that you solve in this.
Gotcha.
So this is the friction. You use these equations here to solve for the friction. And then you plug those into this equation, the force given in the problem minus the frictional force. And that will give you your net force.
Okay.
Ooh, I'm having a sleepy day. Afternoons are always a little bit sleepy, but I prefer teaching in the afternoons when it's hot so that I can come inside where the air conditioning is happening. What do we want to do next? Who else has a problem we want to do?
I mean, I have the ones that I need, but if other people need to ask questions, they can first.
Nobody's asking questions, so.
Okay. Number 9, I just have a couple questions within this.
Okay, number 9. Let's see. If I can show-
Because I got number 8 and 10 correct, but I was struggling with the concept, I think, on a
So
couple
this
of
is
these.
number 9 in chapter 5 here?
Yeah.
I've already done this problem. I must be in your homework assignment here. I'm not enrolled in this course. It won't let me do anything. It doesn't like me. Yeah, I have a message. Number 9. Skydiving. We should do a field trip and go skydiving.
That would be awesome.
That would be expensive.
It's for science.
We'll just base jump instead of skydive.
Okay, slightly less legal, but whatever.
Okay.
The part where it asks in which positions his velocity is constant.
Yep.
Well, I've tried this 4 times, so haven't gotten it right yet.
So, what makes for constant velocity? Or another way to ask it is, when do you get non-constant velocity? In other words, when do you get acceleration? What causes acceleration, according to Newton's second law?
Force.
Yeah, a net force. So if you go to each one of these and add together the forces and find out which ones of these have some net force that's not 0, then all of those you'll be accelerating in. The ones where it adds to be 0, you will not be accelerating.
Right. I thought I had put that as an answer. but, and then number 5, which position is moving at the greatest speed?
In which position is Al moving at the greatest speed? Okay, so which one would that be?
It would be the one with the least acceleration.
The one that he's moving with the greatest speed. Remember, when you're falling, there is a point that you reach where you're going as fast as you can go because the friction from the air is equal to the force from gravity, but opposite. We called that the terminal velocity. And the terminal velocity happens when the friction from the air is equal but opposite to the force from gravity. So which one of those pictures does that?
C?
That's correct. C is the one where you have the force from the air is equal to the force from gravity, so he has gone as fast, he's going as fast as he can go. Can't go any faster.
Okay. So then how is it different from E?
In E, the force from gravity straight down is 1,000 newtons, and the force from the air is 1,000 newtons, but the force from the air is acting on the parachute. So he's slowed way down because he has that parachute deployed. So the forces are still the same, but the force is spread over a bigger area, the parachute in other words. And when you spread that force over a bigger area, you actually get a slower velocity, which is the whole purpose of the parachute, right?
Right.
Yes.
On my own, I said that in the part where it asks in which position does Al experience terminal velocity, I said C, and it said I was wrong.
It said you were wrong with C. And are you supposed to do every answer that is correct, or is it just one? Which one? Terminal velocity.
Down right there.
Okay. So it turns out that there are actually 2 terminal velocities in this one. C and E actually count as terminal velocity. But C is the only one where he's going at his fastest at terminal velocity. Terminal velocity really only means that the upward pressure, the upward force of the air and the downward force of gravity are equal.
Oh, okay, I thought it meant just when you were going so fast.
This one just has a different terminal velocity because the parachute is open.
Oh, okay.
Remember, the equation for terminal velocity does include that cross-sectional area for the flow, for the drag, right?
Mr. Daly,
Yes.
on my number 10, it says that I got all the parts right, but in the little report, it says I got something wrong.
Yeah, I just emailed him about that.
Number 10.
Yeah.
Yeah, it says we're missing one.
Is it another skydiving problem?
Yeah, there's like 2 or 3 in a row.
Sweet. You must like skydiving.
Yeah, we only see however many blanks, and then it says we're missing one question that we haven't answered.
Oh, they just do that to drive you crazy, I'm sure. I'll check it and I'll fix it for everybody.
Okay.
On number 11.
Number
Yeah.
11.
That's my question too.
Like, I think I know what's going on, but I just want to make sure that I'm thinking of it right. So, we're supposed to check the formula that starts with F of K, right?
What is the coefficient of, let's see, the volume of constant speed of however on the surface time, surface time. What is the coefficient of kinetic friction? They want to know the formula for the coefficient of kinetic friction, and then they want to know Okay.
So does it want us to check the formula that has the kinetic friction?
Yeah, they want you to check the equation, the proper equation for solving for the coefficient of kinetic friction.
Okay, and then what does it mean when it says substitution?
And then they want you to, it's a good question. That's not very clear, is it? Must have been more clear when I was looking at it the first time. Let me just take a look at it really quick. Let's see here. What number was it again? 11?
Yes.
Okay, coefficient. Okay, so what they want you to do in the substitution box is they want you to plug in the numbers that you know without units and into that equation that you chose along with the variable that you're going to solve for. They're essentially having you do it step by step.
So they want us to just, as the formula is in the little checkbox,
Yep.
put everything in that we know, and then solve it for that, so that, like, saying whatever the coefficient of kinetic friction is equals this.
Yes.
Okay.
And then in the solve part, they want you to actually solve that equation and write in the whole equation. In the solve box, they want you to write in the coefficient equals whatever number you get. And in this problem, they're not using, when you put in the substitution in the solve box, just use mu. Don't try to say mu sub k, or f. Don't use f sub k in the solve and the substitution boxes.
Okay.
Those ones are just going to have, they're not going to have any subscripts in them. You're just going to put in the variable name, not the subscripts. Just so you know. Anything else on that problem you need help with?
We need to put in like the units, you know?
No units need to go in there. Yeah. Whew. Need a fire drill or something to wake me up.
Beep.
Okay. Who else got a question? Any more questions?
21.
21. 320 newtons of force. Constant velocity push. What is the force of friction? So this one is a bit
Which one are you working on?
21. So this one is kind of interesting because people have a tendency to people have a tendency to really misunderstand how this works. We have a box on the floor. And we're going to push it. And it's going to slide along in this direction, whatever. But the velocity of this is going to be constant. In other words, it moves along at a constant speed in a constant direction. Doesn't change anything. So we say, well, if the velocity is constant, then what does that mean for the? They're asking us for what is the force of friction if the velocity is constant? Well, remember Newton's second law. What does it say? Force equals not just acceleration, mass times acceleration, right? So if you have an acceleration, what does that tell you about the force? You have a force. If you don't have an acceleration, if this is 0, what does that tell you about the force? You don't have a force. So if you have a constant velocity, do you have an acceleration?
No.
Acceleration equals 0, right?
What about for friction?
So that means that in this equation, your acceleration equals 0. So the right-hand side of the equation equals 0, but the left-hand side, we forget that the force does not just mean any old force, it means the net force. So this is the sum of all the forces, and that includes our force to the right-hand direction, that's this one right here, F, which is a positive force. That includes that one, but it also includes the friction. And now you have an equation you can solve. The force that they give you, let's say it's 25 newtons. I don't know what it is. But if the force they give you is 25 newtons, that's your F right here. Then we add to it the friction. We get 0. What does that tell us that our friction is? If we solve this equation.
The same as here.
Yeah, it's actually negative 25 newtons. So in other words, our friction is pointing backwards in exactly the opposite direction. It's the same value. Negative 25 newtons, just in the opposite direction. And you say, well, if you have two forces that are pushing against each other in the exactly equal and opposite, it can't go anywhere. Not true. It can't accelerate, but it can go places it can go whatever it needs to go, but it just can't change its velocity. It can have a velocity, it just can't change it. So it won't slow up, it won't speed down. It won't speed up, it won't slow down. There we go. It'll just remain staying still, or it'll move at a constant velocity, which is constant speed, constant direction. But so that's a tricky one. It does unveil a little bit of a mistake that students often make. I'm going to go and get a bottle of water really quick from my fridge. I will be back in 30 seconds, just so I can wake up. Okay. So now you can just write that answer down, right?
Mr. Bailey,
Yes.
back to number 11 real quick, where it's the second part asked what would the acceleration of the block be if the coefficient of kinetic friction was assuming number changes for everyone. So I have the number. Do I need to put in
Number 11, you're saying?
number 11? That one. So now that I got the first part, it's on the second part.
Okay.
Because it says what would the acceleration of the block be if the coefficient of kinetic friction was
If the coefficient of kinetic friction is 0, what happens to the friction?
well, mine isn't. It's 0.05.
So what happens to friction if it's 0?
The acceleration is constant. Well,
if the friction is equal to the coefficient of kinetic friction times the normal force, and the coefficient of kinetic friction is 0, what happens to the friction? There is none. So then you just go back to your net force just being the applied force, equaling mass times acceleration, and you can calculate the acceleration that way.
Yep. So when you, I have my answer, it's just format for how to put it in. I have the number, but should I put it doesn't have a specific box for, oh, okay, never mind, I didn't have to do all of
I think this one they do want you to say A equals something. So they don't want you to type it in as A equals whatever.
So when I put in A equals my number and then the meters per second squared?
Yes. And they're writing it as meters times second to the -2.
Oh, wow.
I don't know if they'll... Why are they being so goofy on this problem? This problem is a goofy one. I don't think I like that one very much. Hopefully they'll take it no matter what you put in there, but... Who knows? That's why we're beta testing it. Get as much of this weird stuff out of the way as possible. All right. What else have you got for me?
It's saying that I'm not getting
The acceleration is not correct.
No, on back to the first part, like I have the substitution here, where it's the coefficient of kinetic friction equals, and then I put the numbers in where it's so I got the part right where it's coefficient of kinetic friction equals mu kinetic times the normal force. But then when I solved it for mu, it said I was wrong.
So when you solve, which one is it?
Can I bring my computer up to show you?
Yeah, so when you substitute it in, did you solve it with the numbers?
Yes.
So the solve part should just be your coefficient of kinetic friction equal a number.
Equal number?
Yeah,
Okay.
you're actually going to completely solve it. You're not going to solve it symbolically. You're just going to say, what is my coefficient of kinetic friction? Coefficient equals something, some number.
Okay.
Got any more, Cassie?
Yeah, I was just trying to figure out 11 and I'm stuck on that number 2 part.
Okay, so,
It asked me if it was 0.1.
so what would it be if the coefficient of kinetic friction was 0.1?
So would you have to... Oh,
So remember, in this problem here, this is the deal. Right, we got a force pushing to the right, we have a frictional force pushing backwards, but the velocity is constant, right? Is that right? That's the first part. Wait, is that the right one?
no. At a constant speed.
I don't even know what I'm doing anymore. So 400 newtons, it's moved at a constant speed by a force of 60 newtons. So that's right, we have a block that has this weight to it. It's moving at a constant speed by this force 60 newtons. and the coefficient of kinetic friction is pushing back. You've calculated the coefficient of kinetic friction here from that problem, and they're saying, what would happen if that coefficient wasn't there, but there was another one there? What would happen to the acceleration? So your job is to take whatever coefficient of friction they give you right here. In this case, they gave you in this case, they gave me 0.1. Now, I'm going to take that number, and I'm going to put it in my problem right here for the little f. So little f is equal to mu k times n, normal force. So I'm going to put that into this equation down here. But in this equation, I'm not going to have this equal to 0. Net force is not going to equal to 0. I'm going to have my big force given in the problem. Plus, I'm going to have the little force, which I'm going to calculate from mu k.
So is it saying
That's the number they just gave me, the 0.1, times the normal force, which I can calculate from the weight. And that has to equal mass times acceleration, where mass is the mass of this box, and the acceleration is the acceleration of the box. But you're going to end up solving for the acceleration, this one right here. Does that make more sense to you, Cassie, or do you want to go over it some more?
Not entirely sure yet.
Okay.
Someone can go on to something else.
Well, no, let's figure this out really quick. Let me draw a better picture, because this one's obviously messy. Okay.
So that big F, like you had the F plus
Yes.
small f.
That big F is the force that's pushing the box. That's the force you're going to push this way on the box, big F, right? And then there's a frictional force pushing back on the box. And does it say that the box is going at a constant speed at the beginning?
Yeah.
So what we learned from that is that the friction and the big F are the same magnitude, right? They're just in opposite directions. You could say that big F equals negative little f. But that's what we learned from the first part. But we learned that by plugging into the equation, net force equals mass times acceleration, where our acceleration was 0 because we had a constant velocity. Now we go back to this equation and we say now our acceleration is not going to be 0. This is not 0. And we want to plug this in again. Now we say that the force that's being applied to the box plus the frictional force, which is mu, good night, mu times normal force, right? And it's going to be a negative because it's negative. How'd you like that reasoning? It's negative because it's negative. Negative because it's backwards from the positive pushing force, right? And that has to equal our mass times acceleration. So this is our pushing force, this is our frictional force, and this is our mass, and the thing that we want to know is the acceleration. Well, we just were told what mu is, so that's just a number we plug in. And what's the normal force? Well, on a horizontal surface like this, the normal force is just the weight of the box, which they've already given us.
Right.
And then all you have to do is solve this equation for acceleration by dividing both sides by the mass, and you're good to go.
So, like, n is equal to mass. No, see,
No,
I'm trying to figure out what the
normal.
mass is.
So the normal force is equal to the weight when you're on a horizontal surface. Remember that your weight pushes down on the surface, and the surface pushes back with an equal but opposite force. That's the normal force. And on a horizontal surface like this, where there are no forces in the vertical direction except for gravity, the normal force is the weight. And they gave us the weight. Mine said 60 newtons, but I can just plug that in for n and be done. Well, and calculate out the acceleration and be done.
your normal force, your N and your M are the same.
No. Remember, M is mass, not weight. The N is equal to your weight. The weight is measured in newtons. Mass is measured in kilograms. Right?
That's what I thought. So you'd take 350 and divide it by 9.8.
No,
To find my mass?
we don't need your mass. Well, you do need it over here, I guess, don't
Yeah.
you? You will need that there. So yes, take your. So what did they tell you the weight of your box was?
350.
Yeah. So you're right. Divide that by 9.8 to plug in for the mass, but the N is not the same thing.
Right, that's 350.
Okay, right. That's correct. Sorry, I thought you were saying that you were plugging the mass in here for N.
Well, I put in that answer, but it didn't count it as correct, so I don't know.
So you took what's your original force?
The 60 newtons applied parallel to the surface.
So you have 60 newtons.
Yeah, 350 newtons is how much the block weighs, and the force is 60.
Okay, so and then what is your frictional coefficient? 0.1.
Yeah.
So that should be 60 minus 35, which is 25. Is that what you got on the top here?
Oh, I just have another mathematical error. Okay, I got it.
And then you divide by the mass.
Yeah. Yep.
Okay.
Thank you.
Yep.
It's
Yes.
still saying that mine is wrong.
In which part?
The part where it says solve.
So in the end, when you solve, you should say A equals.
No, on solve on part one. I did my
Part one.
substitution.
What's your number? Tell me your numbers again.
So the substitution that it said I had right was 45 equals mu times 330.
Let's see. Okay, let me take that.
And I'm also struggling on finding that acceleration. I'm not sure if I'm just entering the numbers wrong or.
Okay.
It still said that was incorrect, so.
Did you type it in as A equals the number?
Yeah.
I typed it in as A equals the number space M divided.
Oh, and did you put it in your units?
Years.
No, because I didn't have to on the.
Yeah, they do want you to put it
Because
in
their unit
units.
lives.
There isn't the unit I'm supposed to use for you, is there? Okay.
How does that work?
And you put meters divided by second squared and it worked.
No, it did not.
So you did meters times second to the -2.
Huh?
So that's what I was telling you that they put in for their units. They put in meters times seconds to the -2 power. So
That's
meters,
what I put in?
yeah. And that's kind of goofy, but it's still the same thing.
Okay. So what about my mean? It's still saying.
Yeah, I'm looking that up right now. So. It's number 11 still?
Yeah, number
11. All right, let's see what it says here. Oh, you have it right. They just wanted you, this problem was goofy. I don't know why it's being so picky, but it's,
Yeah, so I got that wrong because I didn't put that.
I think what it's doing is it's just rounding to 2 digits on these.
All of them,
Yeah,
because I've been putting it to 3 consistently through the whole program.
yeah, and this one is doing 2, and I think it's just written by a different person who's wanted just 2.
So should I just write it as 2 and see if that works?
Yeah,
And it's counting the hints as part of the problem.
I don't know what it's counting. It has a whole bunch of parts to it, though, doesn't it?
Okay, so should I try, I put them out as 2 decimal places, I fixed the units, I put it as meters times seconds to the -2. Is there anything else I need to fix on it before I resubmit it?
No,
Okay, now we're good.
okay. Did you get that, Cassidy?
No.
The units for acceleration are meters times
yeah.
second to -2. And then the mu under the solve part, they want 2 digits, the round to 2 digits. Also on the last part, round to 2 digits.
Yeah, I got them all correct except the hints or whatever. The hints count as questions.
Do they?
Yeah.
It's kind of goofy. Let me need to change that in the programming. This is number 11, you say?
Yeah.
So like the previews count? Is that what you're saying?
Like, it won't let you go on to the next hint unless you hit submit. And if you don't get it right, it'll put an X there.
Huh. Well, let me go fix that one right now. I'm going to put that one on hold for right now to see if I can fix it.
Okay. That's fine. I got it all right, except so I finished it.
Okay, what else do we want to do?
I just have the last 5 problems left to do, so, and those are the harder ones.
You have them left to do, or you have questions on them?
I have them left to do. I did 25 and I submitted answers, but they weren't correct, so I'm going to go over it again.
Okay. Let's take a look at 25 really quick. So we have this box on a incline, and it's not moving. It's at rest, right? And they want to know what is the force of friction if it's at rest with this mass and this angle. So we go to our whiteboard, I think. Where'd my whiteboard go? There it is. Okay. Can you see my whiteboard? Okay.
Yes.
Here's our incline, angle theta, mass, m. Okay, what forces are involved in this problem?
Friction?
Okay, which way is the friction pointing?
It would be,
Up like this?
no, diagonally.
Okay, from which direction to which direction? Bottom left, bottom right, top right, bottom,
We go to top left.
from bottom right here. So the friction is going this way because even if it's not moving, it wants to slide this way, right? So that's what we call impending movement. So the impending movement being downward to the right, it will want to, the friction will go upward to the left. Now, is this kinetic friction or static friction?
Static because it's at rest.
So friction static. And I'm just going to write the formula right here. US times the normal force, right? Frictional static. Now remember that this has to be a less than or equal to, and technically, this is a less than or equal to friction. This, in other words, this friction can go up to a certain point. It can resist the movement up to a certain point, but above a certain amount of force being applied, the frictional static will give out. There will be no more. It won't be able to apply anymore, and it will start moving and become kinetic friction, right? We're going to use it as an equal sign to calculate the maximum amount of static friction, but that is that. So, what other forces do we have involved here?
Gravity.
Gravity is pulling which way on the box?
Directly down.
Directly down. And that's important. Right? So it goes straight down like this. So we want to use a coordinate system that is tilted with our incline here. We'll call this the parallel coordinate. And we'll call this one the perpendicular coordinate, right? So we're going to have two components to our weight vector. Here's our weight vector straight down. This component is going to be perpendicular, so this will be our weight perpendicular right here. Weight perp. And then we'll have one that is parallel to our surface, so that's weight parallel right there. And I always draw my triangles kind of askew here so that I can always tell which angle is which. This angle theta is obviously the smaller of the two angles here, and that's obviously this one. It just makes it easier so I don't mess up. And that means that my W parallel is going to be opposite that angle, so W parallel will equal W sine theta, right? And my W perpendicular will equal W cosine theta. Now in the past we haven't used both of these all the time, but we will definitely use them when there's friction, because the weight that is perpendicular, the weight component that is perpendicular to this surface is going to cancel out with what other force? There's one more force here we haven't written in. It's the normal force, right? The surface, the inclined plane, is pushing upward on the block with its normal force. And it's the perpendicular weight force that is going to counteract that normal force. Those two are the equal but opposites, right? There's no, if I split this into two different directions, the perpendicular direction and the parallel direction, and solve Newton's law, second law, in the perpendicular direction, there's no acceleration, so the forces, the net force in the perpendicular direction equals 0. And there's only two forces in the perpendicular direction. There's the weight perpendicular, which is pointing downward to the left. I'll call that the negative direction. And then there's the upward to the right, which I'll call the positive, which is the normal force. And that's it. Those are the only two forces in that direction. Those two have to add to be 0, which means that the weight perpendicular has to equal the normal force in magnitude. Right? So we already know that this right here is also equal to the normal force, which is good because we need the normal force to calculate what?
The force of friction.
The force of friction. So that's going to go up here. So now in the parallel direction, the sum of the forces, the net forces, is they're going to be the weight in the parallel direction, which is positive, and then we're going to subtract off the force of friction, static, and that has to equal 0. But the static frictional force has a formula, mu s times normal force, right? And the normal force has a formula. So we get down here and plug that one in, minus mu s, and the normal force is being replaced with this guy right here. So that becomes mu s times W force, the weight, times the cosine of theta, equals 0. And what do they want to know? I don't remember what they wanted to know.
So the normal force is equal to the weight times the cosine of theta?
Yes. And the frictional force is equal to the static coefficient of friction times weight times cosine of theta. And I think that's actually what they wanted to know, isn't it? They wanted to know, no, they want to know the force of friction. So we have to solve for the force of friction. So to solve for the force of friction, we could use this equation. Let's see.
We don't know what the coefficient is.
No, but we do know the weight. And we know the cosine of theta. Right? So we can solve for the coefficient of static friction first, and then plug it back into here. Plug it back in over here to get the frictional force. So we do know enough to solve it. So if we go one more line here on our whiteboard, the parallel weight, of course, is equal to W sine theta. We know W and we know sine theta. W is just M times G, right? Minus mu s W cosine theta. And then we can solve for our mu s. So this will give us mu s. Once we know mu s, then we can plug mu s back in up here to calculate the force of static friction, along with the normal force. You can also say it's even faster, which I was thinking we were solving for something else because I didn't go back and read it. But it would be even faster to just stop right here and say that this one and this one have to be equal, right? Because if you solve this equation, this is the frictional force over here. If you solve this equation for the frictional force, it tells you the frictional force has to equal W sine theta. So you can just use W sine theta to calculate the frictional force, right? So frictional force magnitude is W sine theta. To get the direction, of course, the direction we already figured out was upward and to the left, right? And then they say, what minimum value must the coefficient of static friction have between the block and the incline? So you can that's calculating from the same thing that we just did, that same equation. And what would the net force on the block be if the coefficient was changed to 0.07? You just go back and plug in 0.07 in your equation for the frictional force, and you would calculate the net force on the block.
When you substituted the weight times the cosine theta for normal force,
Yep.
when you go back and you find the force of friction, I struggle with these terms. So normal force is equal to mass times gravity.
No, only when it's horizontal.
Oh, okay, only.
right? The normal force is the force that the surface pushes back on the block with. So in our case, in this particular problem, the block is at an angle, and that's why we tilted our axes, because it's just the perpendicular weight, just this one, that is pushing down on the surface. And so the surface pushes back with a normal force that is equal to the weight perpendicular. The perpendicular weight.
Okay, so when you substitute for normal force, it's the weight of the perpendicular in
Yep.
this case?
So it's just W sine theta. All right, so, sorry, W cosine theta. Was weight
Cosine
perpendicular.
theta or do you sine theta?
The perpendicular one is W cosine theta. Did I write it wrong on here? No,
No.
I wrote it right here. So this is W cosine theta for the perpendicular.
So you said that one of those would just be equal to your frictional force, that'd be W perpendicular.
So that's actually, this one is actually ends up being equal to your frictional force, W sine theta.
Okay.
So in the end, this is equal to your frictional force, static frictional force. And this one is equal to your normal force as already written. So, it's a tricky problem.
And then for the part B, when it says what's the minimum value of coefficient of static and friction, you could just take a frictional force and a normal force and calculate it from there, right?
That's right. If you plug all those forces back into this equation and calculate the coefficient of static friction right there, that's the number you're going to get. Oh, why is it that I'm so tired today? I actually went to bed a decent hour. Ugh. I did get up early, but I haven't done that much today. By the way, in June, I think it's in July actually. Let's check something real quick. In July, I believe, there will be some students coming from the University of California in Berkeley to our town, which is kind of a rare thing. And let's see. Anyway, there are some students coming out. Here we go. It says June 27th. That's pretty quick. Tuesday, June 27th, yeah. So, and that's at 7 p.m. And I would highly recommend that you guys make some time to come to this. They're going to come out and talk about the eclipse. They're doing a citizen science project they're doing an eclipse mega movie. So we're going to take pictures of the sun, probably with cell phones or something. And they're going to try to get people to participate in this, which is fine. But I am going to be acting as some kind of a host for them. And so any activities that they end up doing while they're here, I will be doing them with them. And if they allow me to invite students to it, I'm going to invite you guys to it, since you're my students right now. I'm trying to get them to let us take them out to dinner and maybe take them to the research center across the street, the UNL Agricultural Research Station, for a little tour. So just kind of keep that open on your calendar. So if we do end up with some activities that day, you can go if you're interested. And Cassie, you're more than welcome to come down here if you want for that. It's free, and it might be a really interesting experience. You never know. I'm not sure if that's too long of a drive for you to even consider, but how far away are you from North Platte, Cassie?
Like 2.5.
2.5 hours. That's a pretty long ways.
It's not bad. I could do it.
So if you want to, it'll certainly be interesting. I'd be willing to offer extra credit for something like that, like, I don't know, 5 points on an exam or something, 10 points on an exam. I don't know. You'll have to remind me that I've offered extra credit, because I often forget. You have to remind me.
You said it'd be June 27th. When?
June 27th at 7 p.m. here in North Platte at the college. And most likely we would, if we did anything with them, it would probably be before that. So we would probably do something that's during class. So if you guys decided you wanted to do it, we might do it in exchange for a lab. So instead of doing a lab, we might go do something with them.
Okay.
But like I said, I'm not sure what's going to happen yet. So just put it on your calendar for now. And it might be a great experience for all of you. I mean, I don't know if you've ever been out to the research station to see what they do out there, but they do some interesting things. I don't know if you could imagine people using lasers to do research with agriculture, but they do it out there. And they have some pretty cool stuff. But, yeah, so.
You said that was June 27th, right?
June 27th, Tuesday, June 27th.
Can I have you check one of my numbers on 25 for me?
Sure. 25. Okay, which one?
The first one, the force of friction, I got 153.12.
What's your angle?
19.7. So when I use the weight times the cosine of the angle, I'm supposed to use the weight perpendicular, not the weight of just the box itself, right? Not the box total, but the weight
No, weight
perpendicular.
time. When you do weight times the cosine, it's weight. It's just the weight.
Okay, hold on.
Because that is the weight perpendicular. And for the frictional force, it's actually weight parallel that's equal to it. So let's take a look at this. So this is the math we did. The frictional force ends up being equal to the parallel weight, which is equal to the weight of the box, W, times the sine of theta. So that's what you should use to calculate the frictional force. This is essentially part A right here. You could also do it this way, just a little longer, give you the same answer. But this one will give you it quicker. So your angle's 19.2, you say?
19.7. So from the answer, I now got 15.64.
And what's your mass again?
46.4. Well, that's not me.
Or does it give you the mass of the box or the weight of the box?
They gave me the mass of the box.
So 46.4?
Yeah. So,
So when I multiply those numbers together, I get 153.28.
46.4 times 1.3 times the cosine. I got 428.
So you did the sine of 19.7.
I did the cosine.
Should be the sine.
Oh.
It's the parallel, right?
Yeah.
The sine of 19.7 times 46.4 times 9.8.
Yeah.
It's hard to keep all the little directions organized, but I have good news for everybody, though. The good news is that when we get to chapter 7, there are no more vectors. When we get to chapter 7, we just do everything with energy. We forget the vectors for a little while, which is nice. Some teachers think it's better to start with the energy section and then move to vectors later, but I think it's better to start with the hard stuff. If you start with the easy stuff and then go to the hard stuff, the students will use the easy stuff to solve their answers. But if you start with the hard stuff, then teach them the easy stuff, it's like they get a vacation.
Yep. Mr. Daly?
Yes.
On number, I'm still on 25 as well. On part 1, my frictional force was 57.211. And then on part 2, where it says it's changing the coefficient of friction, it goes to 5.869.
Okay.
And it only goes, it's if I have my calculations right. Like the coefficient of friction in the first part is only 0.292, and it changes to 0.04. Oh wait, that is a good change. Never mind. Sorry.
Okay.
I tend to do this a lot where I like ask a question, talk it through, and then realize
Yep.
what I did wrong.
That's fine. That's a good thing.
If it's not moving, it has no acceleration, right?
That's correct. If it's not moving, the acceleration is still 0.
Okay. So then what, it says to pick a direction that my non-existent acceleration is going.
Okay, so if they change to the coefficient of friction, it's possible that it could be accelerating. Because they've changed the coefficient from 0.29 something to 0.03. Coefficient of friction is almost non-existent now. So it could be sliding. So you need to change your equation. This equation right here, you need to change it to be equal to mass times acceleration now. And then calculate that acceleration.
So
Because it's very likely going to accelerate at this point.
So I say that my weight parallel minus the
Static friction. Yep.
now is equal to mass
Times the acceleration. That's right. So for that last part where they change the coefficient of friction on you, this equation changes, and instead of being equal to 0, it's equal to mass times acceleration. And you have to change the coefficient in the frictional force. This thing right here has to change to the number they give you. You'll still have the same normal force, you'll still have the same parallel weight force, but you will have a different coefficient of friction and you will have it equal to mass times acceleration.
Isn't the weight parallel? Isn't that the same as the static?
When it was sitting
That's the
still,
frictional force.
when it was sitting still, it was the same.
Okay.
Now that it's moving, it is not the same anymore.
So I would take,
That's why it's moving, in fact.
yeah. So the weight parallel is still going to be
The value that it was before.
okay.
Yeah.
So like in mine, it's the,
That first thing you calculated.
yeah, it's the weight times the sine of theta.
That's correct.
Okay, so, and then the friction, static friction, you still find the static friction, not kinetic friction, right?
No, now that it's moving,
You find
it's a kinetic friction, but it's it's the same equation, it's
Okay.
just a different coefficient. So all right.
And is my normal force still going to be the weight perpendicular?
Yep. Normal force doesn't change. I was going to shave my head today, but I bashed my head on the wood in my new addition, so I've got this big old cut on my head. Not sure if I want to expose my cut by shaving. Are we done, or do we want to do some more?
I'm just writing this down and having a question shortly, I'm sure.
I should probably ask about the other ones too. I'll just have to finish this one later.
Do you have any questions, Packer?
I'm good for now. Would you be able to take a look at number 13, please?
Number 13, huh?
Give me just a minute. I switched windows before I had.
So you still want to do 13?
Yeah, I just switched windows before I answered 25, so I gotta write down, make sure I know what the answers are.
Okay, so we have 114.7 kilogram. Traveling east receives a push to the east. So it's already moving. And there's a friction. We want to know the net force on the object. Okay, so let's go here. Do that. So I think, Cassidy, I think you can actually draw on this whiteboard with me from your computer. I don't know if that's true, but I think you can.
I don't know how. Few
We could have
options.
like whiteboard wars, right? Okay,
Oh,
so here we go. Here's our box. It's already moving to the east. This is going to be east. And then we're going to give it a push force, right? But there's going to be some friction. That's going to be kinetic friction, right?
Mm-hmm.
Hey, she's drawing on my board. Apparently she
That's
can draw on my
cool.
board. So force pushing east, kinetic friction pushing west, right? And they tell us the coefficient, mu kinetic,
Yeah, they
and we have a normal force. We know the mass, right? We know the mass, so we can calculate the weight as m times g, right? So what other force are we missing from this problem that we need? The normal force, right? Because we need that right here to calculate the kinetic friction. So the normal force, which points perpendicular to the surface that something is in contact with, in this case that is up, and in this direction, in the up and down direction, is there any acceleration?
No.
No.
So it's going to be the same as.
So these things have to cancel out. In other words, the sum of the forces in this direction has to equal the mass times the acceleration in the up and down direction, which is 0. So that means they're equal to each other. So that tells us that the normal force magnitude is just equal to the weight, which is just mass times gravity. Which makes this equation easy. Mu k mg, right? And the net force, what is the formula for net force?
Mass times acceleration.
No, well that is Newton's law, but what does net force mean? It means you add them,
All
right?
the forces.
So the force, which the pushing force, that's positive. The frictional force, which is negative. The pushing force is the number they give you. And then you subtract off that frictional force where they give you the mu, multiply that times the mass, and multiply that times gravity, and you're done. And that'll give you the net force.
Okay.
What number is that?
That was 13.
13.
And it's the same for 14 through 16.
Yeah, I gave you a few of those where you're just learning to calculate the net force or the coefficient of friction or the frictional force. It's just practicing calculating that force, because the trick really is to remember that you have to have the normal force to calculate the frictional force. So you just go through and you figure out the normal force really quick, and then you plug it in and calculate the frictional force. They're not difficult problems. They are calculation problems, but they're not difficult. Just to help you to remember the frictional force requires the normal force.
I just want to run one of these just to make sure that I'm doing it.
Hey Packer, what time did you need to leave?
5 would be best.
Okay. I didn't put your stuff in the fridge because it's just packed with ice packs. And you got some Jiffy Pop. I also found those really long hot dog skewers while I was cleaning the garage the other day. I didn't bring them, but if you just to remember that they're between the house and the old house wall and the garage wall where my recumbent bike was. Just drive safe, be good,
Thank you.
have fun.
See you, Patrick.
See you, Andrew. Good luck at speech.
Thanks.
We have all kinds of people going different places this week. Where is the speech tournament?
Birmingham, Alabama.
Alabama.
In June. And it's Sioux. That's going to
Yeah.
be lots of fun.
You're gonna come back all waterlogged.
Pretty much. Okay.
Can I have you check number 25 again on part B?
Could I ask you a question?
Sure.
Yeah, he can go ahead.
Yeah, go ahead.
So if I get a negative net force, that would mean that it isn't moving east, it's moving west.
Not necessarily.
That just means
It just means that it's slowing down. Right?
So so it's slowing down and going. So my net force would be pointing west if it's slowing down.
Yes. All right, so we're going to check out number 25, you said?
Yeah. I feel like I don't have this right, but
These ones here.
well, 0 is not my answer now. I typed that in, that was wrong. So. When you're trying to find the minimum value before it'll move, don't you, like, do I use the force of friction that I already calculated?
So the minimum value between the block and the incline is actually the one that you calculated. Oh shoot, I lost that one. That one is the one that you calculated from the force equations in the parallel direction. So it would have looked like this.
The weight to,
You would have you'd have the weight in the parallel direction pointing down this way. You'd have the frictional force pointing up this way, right? Static friction pointing up this way. And what it looked like in the end is it looked like the weight parallel, which was weight times sine theta, right?
mm-hmm.
And then minus the frictional force, which was mu static times the normal force, which was the weight perpendicular, which was weight times cosine theta. And then that was equal to 0. Right?
Yeah.
And if you solve this equation for mu sub s, you will get the correct answer.
I got 0.36.
And that is correct.
So then part C, is it 8.56, or did I do that wrong?
Part C.
Yeah, so that's what the net force would be if,
No, the net force on the box is going to be actually, let's see, part C says, so that is if you change mu sub s. So for part C, what you do is you come in and you put 0.3 into here instead of the number that you just calculated, or 0.02 rather, because it wants you to change it to 0.02, right?
mm-hmm.
So what you do is you come back and you put in 0.02 right here in the mu sub s, and then you calculate an answer from here. And that'll give you some number that'll be much bigger than
Yeah.
what you have. Does that make sense now?
Yes.
And then for part D, you use that number because that's now your force, and you put that number, force, into the equation force equals mass times acceleration and solve for the acceleration for part D.
And you would just use the regular mass, correct?
That's correct. In that case, you just use the mass of the block.
I think at a certain point I just get burnt out.
It's easy to get burnt out. It's not abnormal. And this is actually one of the reasons that I decided to just try to teach Mondays, do lab Tuesdays, teach Wednesdays, and then have the rest of the week off. Because we can just go for a little while and then stop and rest. And not have to beat our heads against the wall too much. The real problem is that if you take too much time between working, then you forget things and you have to start over. But if you take too much time working on things, you burn out and you're just dead. So you have to have a balance. So that's why I did Monday, Wednesday, and then break. Monday, Wednesday, and break. I do that during the school year as well. We only meet twice and have a lab. So.
Okay, 26, here we go.
you have a question on 26, or are you just starting it?
I'm just starting it. Okay, so part A, when it's asking for the weight of the car, it's not asking you to split it into perpendicular and parallel.
So this is 26.
Yeah.
No, they just want to know the weight of the car. So let me just check that really quick.
Big paragraph.
So the weight of the car. $26 per A.
Part A would just be mass times gravity, right?
I am assuming that, but I'm just checking to make sure that they're not doing something goofy. Yeah. It's just, in this case,
Mass times gravity.
0.9, 1.8. Yeah.
What about part B here? What's the, basically like a normal force so that the car doesn't move up or down on the track at all.
With no friction.
So do we need to find a perpendicular normal force?
So in this situation, what they're saying in this can be a little confusing because you have to draw a picture. So let's draw a picture. How come I can't get to my whiteboard? Okay, so let's draw a picture of this. So here's our incline. Here, still don't like it. I want to make it even shallower. Okay, so here's our incline, and our car is here. I'm going to draw it as a block.
Would you do it with the screen right now?
Yes, sorry.
Thank you.
And normally, if you're just sitting here, you're going to have some forces. You're going to have the weight going down this way. You have a normal force going perpendicular to the incline. And then you're going to have the frictional force. The car is going to be trying to slide down towards the bottom of the track. So the frictional force is actually going to be pushing up on the car this way. Okay? So that is the picture of the forces that we've got here. What they're saying is that at some point in this, the life of this car, there is no frictional force required to hold it up.
On this, it sounds like you're saying it's because it's moving, right? So that it's almost like the, what's it called?
What they're saying is that as the car goes around the track, of course its weight stays the same, right? but the normal force increases. And that's because there is another force involved here that we haven't taught you about yet. And that other force is called the centripetal force. And that's the force that causes the car to turn. So what that means is that there is another force here involved, and that other force pushes the car towards the center of the track, which is this direction. And that's the force that causes the car to turn. This, if we consider our coordinate system to be like this force right here is actually going to have a component that it pushes up on the car this way. One component that way and one component this way. And that upward component adds to the original normal force. Here's the original normal force. Here's this extra little component. So our normal force ends up being bigger than it was before. And that's what they're saying is going on here. So with a bigger normal force here, it changes things a little bit. And let's see here. So let's go back to the problem and see what they're asking for really quick. And
It's asking what's the normal force of the car in this situation.
knew that the car wasn't moving. The problem car is currently moving. The car, so the driver wanted to go around the turn at perfect speed. The car would want to slide on the bank. Okay, so what we do, we don't even need to know about the other force at all. All we need to do is realize that what they've asked us, the problem they're asking us to do is this one, where the normal force is bigger than the weight of the car. And so let's just go ahead and do that. Let's go ahead and clear this and start from the beginning. They've just told us the problem we want to solve. The problem is a problem where there is no
friction.
no frictional force, right? And that's fine. We can live with no friction, right? But what they have told us is that the weight has its normal value, its regular value, but the normal force is bigger than that. So let's put that normal force up here as bigger than that. Okay? And what does that mean? Well, what this means is actually that the force, this means that there is an acceleration on the car. What is the acceleration?
It's the energy.
It's the turn.
Oh, okay.
Remember that turns are an acceleration as well. But there is no acceleration down. There's no acceleration downward or upward. Let's see if I'm drawing this correctly. I'm not drawing this correctly.
Did we talk about centripetal force?
No, we didn't, and that's why I erased that previous picture. So here is our parallel, and here's our perpendicular. Let's see if we can draw it this way. So here we have a component for our weight. That's our perpendicular component. Here we have a parallel component for our weight. Weight parallel. And then this normal force one, this one is just completely perpendicular, right? Yes. I don't really like the way that's working out for us. So I'm not going to use, so this is not really going to help us much, in fact. You might go immediately to this because you have this incline here, but if we notice, all this really tells us is that the normal force is bigger than the perpendicular weight component, which we already knew it was going to be because it's bigger than the normal weight component. So we already knew that. So that's not telling us anything new, and it's not going to give us anything we can solve. all this is going to say is that if we add this normal force and this weight force together, we're going to have an acceleration. We already knew we were having an acceleration. We know the acceleration is going to cause this thing to turn. So let's not tilt our axes. Let's actually undo these, and let's look at this from an untilted axis point of view, which is what I was doing to begin with. So let's look at it with our x and y axis, normal old axes that we always use. And let's look at the components now. Is this car going to accelerate up and down in this direction, in the y direction? It is not, right? It's going to stay at that same height on the track. So in the y direction, we already know something. In the y direction, we know, so this is our normal force, that this is the normal in the y direction. We know that the normal in the y direction minus the weight of the car has to equal the mass times the acceleration in that direction, which is 0, because it's not going to accelerate in that direction, right? Up and down, the car doesn't go anywhere. So that's good. So normal y minus the weight. Well, what is the normal y? Well, this is the angle theta here. And that means this is our angle theta here. The normal in the y direction is going to be adjacent to the angle theta, so it's going to be the normal force times the cosine of theta, right? So now this equation is the normal force times the cosine of theta minus the weight, which is m times g, equals 0. And there, what do they want to know? They want to know the normal force. We know everything in this equation. We know the cosine of theta, we know m times g, so we can now solve for the normal force and get that answer. Right? We add m times g to both sides, we divide by the cosine of theta, we plug in our numbers, and we get the normal force.
Where the mg is just the weight of the normal, the original normal force?
No, the mg is the weight of the car, which is not the normal force.
Okay.
It's only the normal force if you're horizontal.
I guess I'm confused as to, so you have your, I'm just laying it out step by step. So I'm going my cosine of theta equals the normal force for y over, and it would be your normal, wouldn't it?
So the triangle that we're looking at is now this triangle here. This is our normal force. It is perpendicular to the surface, right? Mm-hmm. And we are looking at the y component of the normal force, which is this one.
Yep.
Which is adjacent to the angle theta here. Since it's adjacent to that angle theta, the normal, which is the thing we're looking for, this long, big old vector here, times cosine theta, will give us ny. N cosine theta. Plug that in over here. Well, over here. And we get n cosine theta minus mg equals 0. Solve for n, you add mg to both sides, divide by cosine theta on both sides.
Oh, okay, that makes sense.
Okay? Does that make sense to you, Cassidy?
Yes.
All right.
So that's considered that's our normal force.
That's correct. Now, think of it this way. Have you ever been in a roller coaster?
Mm-hmm.
When you turn a corner that's banked like that, that's at an angle like that, do you feel heavier?
Yeah.
It's not because you're heavier. You didn't gain weight. You don't have to worry about anything. You know, you don't have to stop eating corn dogs at the fair just because you went on a roller coaster. What is happening is that the roller coaster the normal force from the roller coaster is pushing upward on you harder because you're turning in that curve. And that's exactly what's happened here. This normal force got bigger because of that turn. So the force of the curve pushing into the car is what turns the car. That's actually what makes the car turn. So it's actually not you feeling, it's not you getting heavier, it's the car being pushed on by the ground. And you're in the car, so you feel that push and it makes you feel heavier.
So that normal force would be going at a diagonal direction?
This one right here, that is it right here. At a diagonal direction towards the center of the turn. And perpendicular to the bank of the turn. So the upward part of it, the upward part of that is the thing that holds the car, keeps the car from sliding down, right? The inward part of it is the part that turns the car around the circle.
So, when we look at part C, wouldn't your net force be equal to, or not your net force, your so we know that our normal force is, so we know what our normal force is.
Yes, part C says, what is the net force on the car? This will be equal to the component of the normal force that is pushing the car towards the center of the turn, right?
So that would be normal X.
So that's your normal X force. So you got to go back and take the normal that you just calculated and multiply it by the sine of theta instead of the cosine of theta. So that's this one right here. So you take, so on the other side of this, you have this n sub x up here, which is opposite the angle theta, and n sub x equals, and the normal force that you just calculated in part B times the sine of theta. And that's your net force on the car. This is a tricky question.
So should the net force be considerably less than the normal force?
Yes, it will be less.
Okay.
So what is our X being in this equation? Like what is it?
X
This
is
normal
the
X force.
yeah, it's the X is the horizontal direction, just like it usually is. And the normal X force, or the X part of the normal force, is that force that pushes you towards the center of the turn.
So that's
causes the turn of the
Our
car.
net force is pushing it this way towards the center of the track.
Yes.
Okay. And then centripetal acceleration.
So centripetal acceleration is just, you take that n sub x, or that net force towards the center, set it equal to mass times acceleration, and solve for the acceleration. Centripetal just means center pointing acceleration. So for the last part of it, you take this force here and you put it into force equals mass times acceleration. So it ends up being n sine theta. This is for the centripetal acceleration. N times sine theta equals your mass times your acceleration centripetal, and you solve for that in this equation. And that will give you the next part. Now, technically, that question, I suppose, should be in the next chapter. But it's close enough to what we're doing that I'm not going to worry about it too much.
This part E here, we're asked about the radius. Would that, since it's using radius, is that Stokes law by chance?
No,
Okay.
it's asking for the radius of the.
It's asking what's the perfect speed that the car would need to be going in order to not utilize friction.
Let's see here.
Did we already find that? Or
150, 22. That is. Shoot. was hoping they wouldn't ask that question. And I didn't obviously look all the way through that question. Because now that they asked that question, we have to go to the next chapter.
So do you
Which
want us
one?
to- Do you want us to just submit what we have and you can correct it, or?
Yeah.
So
The last part of the question asks what the radius of they tell you what the radius of the track is, and they ask what the perfect speed would be for the car to not have to have friction. But to do that, you have to know something from the next chapter. So
Submit what we have?
yeah, just submit what you have, and I will grade it by hand.
What is the direction of the centripetal acceleration?
So the acceleration is the force that's the centripetal acceleration. Centripetal just means center pointing. So it points towards the center of the turn. So if you're turning around, let's show my whiteboard here. So if this is the circle that you're turning around right here, and that's the direction that you're turning, here's the center of that circle. Your centripetal acceleration will always point towards the center of that, no matter where you are. Does that make sense? So in the case of our car, it's pointing this way. To the right. Because the center of the turn is here. The car is going around in the circle. The center of the turn is over
Because
here.
it's facing towards us.
Yep. So centripetal just means center pointing.
Oh my gosh. What's the number force in the car? Okay. My goodness. Okay. 17. Okay, 27. So the 2 minus 1.
I'm looking at 27 here.
27?
Yeah, it has like the two boxes that are connected with a connecting rope, and they have different masses. And it's asking, it gives the frictional coefficient, and then asks what's the maximum value which the combined frictional forces can fight this pull. So is it basically asking final frictional forces for both? Oh, this is pull. Slightly far out.
Yeah, there's a pull. There's two boxes. They each have a friction associated with them. So they have the same coefficient of static friction. And what maximum value with the combined frictional forces can fight this pull. So you're going to calculate the maximum friction, static coefficient of friction, or the static friction that they
For
can.
both of them?
Yeah.
So like take for mass 1, for mass 2, and add it together?
Yep.
Okay, and since the friction that both of those boxes have is less than what's pulling on them, it's starting to move, right?
That is correct. Let's see, what is today? Tuesday? Wednesday. So it is 5:27, and I am sorry to say that I have to leave on time on Wednesdays most of the time. Well, not most Wednesdays, but this Wednesday I do. Next Wednesday I won't have to. The Wednesday after that I won't have to. The Wednesday after that I won't have to. But this Wednesday I have to because I have to go to Scouts. I am the Scoutmaster, so I have to go to Scouts tonight. Are there any last questions before we end this party?
I think on 27, I can figure out part C. What would you do for the tension on part B?
Well, the tension in the rope is going to be caused by some forces, right? And you can either calculate it from the pulling force or from the frictional force backwards, one or the other. So,
If I have any questions, I'll email you.
okay, sounds good. So at the point where the hand is pulling on the rope, if you consider that your system, then you have the tension pulling one way and the force pulling the other way. And those two forces have to add together to equal the mass times acceleration, and you can use that to solve. Which you've already done, essentially. You just need to write down the answer,
Okay.
if you got that far. Okay. I will be available for emails and everything else, so feel free.
Will do. Thank you so much.
Have a great end of the week, and we'll see you all next Monday.
So,